I spend a lot of time thinking about the universe, but I never get bored. After all, it's a pretty
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
I'm going to explain to you what's known as the central mystery of quantum mechanics. It was Richard Feynman, the American physicist, said, this is the central mystery of quantum mechanics. There's lots of weird stuff that goes on in the quantum world. Hit you with this, and it basically tells you what it's all about. It's called the two-slit experiment. I'll start with this. Imagine you have a source of light shining against a screen with two slits. Now, for the pedants in the audience, this source of light has to be monochromatic light, light of a particular wavelength, whereas, of course, a light bulb is white light, and that's made up of all the colors of the spectrum, lots of different wavelengths. But imagine this is just a single wavelength of light, and you can see the light is coming out in waves like ripples in a pond. That's the nature of wave-like behavior. As the light hits the screen, it squeezes through the two slits, and each slit in turn on the other side becomes almost like a new source of light, and the light spreads out, it diffracts. And as the waves of light overlap, they will interfere with each other. So where a crest hits a trough, they will cancel. Where a crest hits a crest, they will amplify, and so on. And so on the back screen, you end up with what's called an interference pattern, a series of light and dark fringes, where the waves have either cancelled out or worked together in phase. That's fine. That's not quantum mechanics. That's a property of light that goes back over 200 years that we've known about since the early 19th century. Imagine doing the same experiment again, but doing it not with waves, but with particles. Do it with grains of sand. So this is the same experiment, but I've tipped it 90 degrees. Rather than waves that are spread out that wash up against the two slits and squeeze through, here you've got individual particles of sand, and each particle will either go through one slit or the other. And so you see they will sort of drain through, and you get two bumps underneath each of the slits. So the two peaks is reminiscent of particle-like behavior, whereas the multiple pattern of interference is wave-like behavior. What if we do the same experiment with atoms? Well, so imagine we have an atom gun, something that can fire atoms, a stream of atoms. You can't see them because they're very small. Let's block off one of the two slits. So these two slits are the dimensions and separation of the slits is chosen appropriately to show us how atoms do things. And so far so good, nothing strange here. You'll see a lot of atoms hitting the back screen. So this will now have to be some sort of photosensitive screen whereby when an atom hits it, it'll give off a little flash of light to say the atom has arrived here. So the atoms are arriving as these little pinpricks of light that we see. Of course, a lot of the atoms will be blocked by the first screen, they won't go through that slit. But those that do get through to the other side, you can see there's a bit of spreading of the atoms. But if we didn't know anything about atoms, we'd say, well, that's fine, we can understand that. A lot of the atoms are going clean through the slit. Some are sort of maybe bouncing off the edge of the slit, and so they're sort of being deflected a bit, which is why you get a bit of a spread. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves, and you get interference of the waves and you get these bands. If we know nothing about atoms or quantum mechanics, you could try and rationalize it and say, well, you know, maybe atoms behave in a very strange way, and only a certain number of them are allowed to all sit together. And so, you know, me and my gang, we're all going to go on this slit. No, sorry, no room for you. You go to the next slit above. And by the way, there's this rule that no one can go in between the two bands, but a few naughty atoms do. So there's a bit of a scatter. You know, we don't. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. That's not mysterious. That's just, we just don't know how atoms do things. But we can be clever, and we can force the issue. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course,
Here's another little interesting experiment that has been done many times. There's an appearance of backward causality. And one of the first times it was done in an Israeli hospital. It's since been done with decaying radioactive substances, and they get the same result. But I'm going to go over the one with the hospital stay. You'll find it real interesting. I think it was a group of rabbis and other people who were interested in metaphysical things, and they collected data from a local hospital of all the people who'd been there over a length of time, over the last 10 years or something. Then randomly, they selected from this data a group, let's say half of them, and the other half then were the control group. So they just randomly picked people out. Then they prayed for the health of these people. Okay, they focused their conscious intent, okay, in my terms. And they did this for a while over these people. Now this is data that's 10 years old, okay? This is old data. So they then prayed for the health and well-being of these people. And then what they found out was that the people in their experiment group that they had prayed for had a statistical significant difference of shorter hospital stay. Those people that the intent was applied to had I think it was it was enough percentage difference to be statistically significant. And that was like, wow, how did we do this? Now this was old data, how did we affect this? So they tried it different ways. They would take another set of data, randomly do that, and this was done a dozen times. And every time they got the same answer. The group that they applied their intent toward having good health ended up with a shorter, on the average, shorter hospital stays than the control group. And it was like, wow, we're changing things in the past. This is backward causality. Well, it's not backward causality. They're not doing that. They're not doing that at all. A similar thing was done with radioactive decay. They took radioactive decay, and if you can imagine a radioactive substance, and it kind of randomly spits out particles. You don't know exactly when these particles are coming out. It just happens. So they use a Geiger counter or some way to intercept this radiation, and they look at the time intervals between getting a reading of some particle coming out. Well, then they take a lot of data. You take hundreds of thousands of these points of data, and you can average it, and there's some average time that it takes between particles. Well, they would do the same thing as they did in the hospital. They'd take all that data, they'd separate it into various pieces, and they would have people with their minds intend for that data to be a little above the average, it took a little longer, or a little below the average, came out a little shorter, and they found out they could do that. And this experiment has been repeated many, many times. So they can actually shift the average a little. Not a lot. It has to be within what is reasonable. Science certainty principle, not going to let you shift it, but so much. And here's basically the way that works. Let's take the hospital thing first, and let's say we have 20,000 patients. Okay, and let's make those 20,000 patients into 20 groups of 1,000. Okay, now let's take those each one of those groups of 1,000 and break them in two. So now we've got 500 and 500. Now the way it worked is that then they prayed for, say, that 500. And if it turned out that the average hospital stay of the group that didn't get prayed for then tended to be a little longer than the average stay of the one that did get prayed for. And the difference wasn't so much that it would be remarkable for that group. The difference was maybe, 2 or 3%, 4%, something like that. But then they did the same thing in the next group, and it was a few percent. And the next one, and it was a few percent. What you would expect is some of them would be a little high, some would be a little low, because statistically, you're not going to get to hit an average directly. That average could be calculated to 10 decimal points, decimal places. So you expect to fall a little bit to one side or the other, but you'd expect as often to fall, to the high side as you would to the low side. Well, they fell, as far as hospital stays, to the low side 20 times in a row. So none of them were more than probably, 3 sigma events. Well, that's not a big deal. Statistics will sometimes give you a 3 sigma answer, but 20, 3 sigma events, now suddenly you got something that
Quantum mechanics can be both strange and baffling. Sometimes, studying quantum mechanics, you feel a bit like Alice in Wonderland, as if you've fallen down the rabbit hole. And one of the most amazing things about quantum mechanics is that of entanglement. My name is Dr. Chris Dersham, and today I'm here at the Institute for Quantum Computing to try and answer the question, what is entanglement? Come on inside to one of the labs and let's see what we can find. When two objects are entangled with one another, they share a peculiar connection. For example, if I were to take these two molecules and entangle them with one another, I could then take them to opposite ends of the universe, and yet they'd still be connected. Anything I did to this molecule would instantaneously affect this one. Einstein so disliked this concept, he termed it spooky action at a distance.
Nein, ich mag diese spukhafte Fernwirkung nicht. Nein, nein, nein!
Entanglement was the subject of some of the most vigorous debates between Einstein and Niels Bohr, and has played a profound role in the foundations of quantum mechanics. But what's entanglement good for? Well, using entanglement, two people can share secret messages between them. Or you can use entanglement to build a super fast computer capable of solving problems that today's machines can't handle.
Most physicists agree that the math is quite solid and leads to solutions that are undeniable and can be confirmed with experimental measurements. But exactly what is happening and how is a matter of debate.
To try to grasp this amazing experimental result, scientists decided to observe how individual electrons behaved when they went through the double slit. How exactly could a particle go through both holes at the same time?
Scientists got a front row seat to observe the strange behavior of these electrons or other subatomic particles or even photons of light. Doesn't really matter as long as they're small. They didn't just look at where they landed on the screen back there. They also watched the behavior of the particles as they went through the holes. And then they saw something amazing. When scientists were watching the holes, the electrons behaved like particles, forming the baseball-like pattern on the screen back there. But when the scientists weren't watching, then the electrons behaved like waves. They formed a pattern that looked like the interference pattern produced by waves on a screen. That's really strange. What you see depends on whether you're watching or not. If you're watching, you see the particle-like behavior, like baseballs. If you're not watching, you see a wave-like behavior, but not both at the same time.
This was nothing less than astounding. Observation seems to change the nature of subatomic particles.
Mysteriously, when we're not looking, things are waves. When we are looking, they look like particles. So even an electron, which seems to us like a particle, has wave-like properties when we're not looking at it.
The subatomic version of this baseball can be invisible, can go through solid objects with ease, can be in multiple places at the same time, and can seemingly go backwards in time and change the past. This means I could throw this microscopic baseball to first base and to home plate at the same time, or change the seemingly predetermined outcome of a play while it's still going on. Now, this is the stuff of science fiction, but really, we know it to be true, or at least it appears to be true in our quantum world. We get all sorts of weird things happening.
If scientists can understand how these weird things work, they'll be able to put them to use in our everyday world, revolutionizing modern computing, and perhaps even allowing us to communicate across the cosmos instantly. The key to making these miracles come true is a process
there was nothing.
Somehow, out of this nothing came everything.
Out of this vibrant nothingness, matter, energy, space, time, consciousness, mind emerged, came out.
How is it that something as unconscious as the matter of the brain can ever give rise to something as immaterial as an experience?
If you want to see fear in a quantum physicist's eyes, just mention the words, the measurement problem. The measurement problem is this: an atom only appears in a particular place if you measure it. In other words, an atom is spread out all over the place until a conscious observer decides to look at it. So the act of measurement or observation creates the entire universe.
Only conscious beings can be observers, then we're intimately hooked into the very existence of reality. Without us, there would just be this expanding superposition of possibilities with nothing definite ever actually happening.
Out of millions and millions of blobs of energy and light, photons and electrons, they make up this imaginary three-dimensional solid world, which doesn't exist at all according to relativity or quantum mechanics.
Anytime we attempt to look at particles beyond a certain level, the very act of observation changes things.
And in addition, the more you look at individual particles, the more you realize that there is no such thing as one electron. An electron, or any elementary particle, exists only in relationship to other things, like other particles or the universe at large. This means that deeply enough, when you dive down into the nature